A timeless landscape, clues buried in the past, and discoveries that can build a better understanding of our climate. Jihong Cole-Dai, a professor of chemistry at South Dakota State University,
fix the scale,
has embraced the challenges of fieldwork in the Antarctic environment and found evidence of a previously undocumented volcanic eruption.
Yes, that's a standard.
Why does a 200-year-old volcano blast matter today? Scientists already know that a large volcanic eruption, Tambora, in 1815, cooled our planet. Tambora has been credited with causing the so-called year without a summer in 1816. The volcanic eruption identified by Cole-Dai is thought to have taken place in 1809 and may provide additional information about this type of global temperature shift.
You want to set up the...
By looking at ice cores that offer a chemical timeline of atmospheric events, Cole-Dai says we can learn how naturally occurring events impact climate change.
To sort of know what we're going to be facing in the future, we need to be able to predict what the climate will be next 50 years, 100 years. To do that, we really have to understand how nature works on its own in terms of climate change. One of the reasons that the climate changes naturally is because of volcanic eruptions. Usually a big volcanic eruption goes off, it puts all these chemicals in the atmosphere that act as a sort of a reflector that reflects some of the sunlight so that the Earth usually cools off.
Cole-Dai and graduate research assistant Allison Linsicki have moved and melted tons of ice core samples from the Antarctic and Greenland in order to find these chemicals.
If you come over here, I'll hand this to you.
In their research, they hunted down specific evidence: sulfur isotopes and materials changed by exposure to the stratosphere level of our atmosphere. Finding these microscopic substances in ice meant that they came from a volcanic eruption large enough to send sulfur and other materials high into our atmosphere above the clouds.
We took about 5 tons of ice, which for chemistry is a big amount of sample. And for each volcanic event that we analyzed with the sulfur isotopes, we had to get at least 2 samples per event, and the size of the sample at the end, after all the conversions and basically boiling them down, was about 1/4 of the size of your pinky nail after a couple tons of ice. It's kind of a challenge to go through it and figure out, how am I going to do this? How do I get contamination out of this? You've got to be very cautious about every little step of the way, and very, very cautious about losing some of your sample when you've got such a little amount at the very end.
Cole-Dai worked with colleagues to conduct research funded in part by the National Science Foundation. NSF infrastructure geared to support Antarctic research made gathering samples in such a challenging environment possible.
If you're out there, you need food, you need fuel. Sometimes you need people to help you to move things. They are specialized companies that contract with the NSF and do that type of support for our projects.
Cole-Dai says that thorough planning is perhaps the most important part of undertaking research efforts in such a hostile weather environment. And while it may be more common to think about research chemists in lab coats than in heavy-duty parkas, Cole-Dai says that new ideas can form at both the ice cap and the lab bench.
When things get hard, I tend to think about, what we will be able to do with the ice samples once we get them into our lab. It's very exciting to think about the discovery you can make with the ice samples, and so that makes all the hard work worth the effort.
For South Dakota State University, I'm Tami Watson.